what happens here is there are two mixtures of water, right? There was a mixture of two water at two different temperatures. So there's a mixture of water at two temperatures. So we've got cold water and hot water. So remember we talked about transfer of energy from cold to hot objects, and this applies, even though I've drawn a picture that looks like solids, this applies regardless of what kind of material it is, so what phase of matter you're talking about. So in other words, there will be heat transfer from hot objects to cold objects for solids that are in contact, liquids that are in contact, and gases that are in contact. So reminding ourselves of the law of conservation of energy, this basically means that the bath water is heated by the hot water because energy is transferred from the hot water into the cold water, which does two things. One, hot water temperature decreases, goes down, and two, cold water temperature increases until they are in thermal equilibrium. Which means basically that both of these, the hot water and the cold water, will be at the same temperature. Thermal equilibrium, if you are unfamiliar with this term, you should look it up. It basically means that two objects in contact are at the same temperature so that there is no energy transfer between them. So as you know, there's always energy transfer if two objects are at different temperatures. So if they are in thermal equilibrium, it means they have reached the same temperature. Okay, so recapping, hot water is going to be mixed with cold water, and energy transfers between from the hot water into the cold water until they reach the same temperature. So in other words, the hot water loses energy and the cold water increases in energy. Now, we know that the increase theoretically should be the same as the decrease because of the law of conservation of energy. But let's think for a moment about what happens in the real world. So in the real world, if you have hot water, eventually it will cool down even if you leave it out. So where does that energy go? And I hope your answer will be it comes from the environment. So if we want to do this problem, then we're kind of assuming that this transfer occurs in a closed environment. So we're talking about a closed system. So no energy escapes from the system, from our hot and cold water mixture or bath. So that's one of the assumptions. No water is lost, no energy is lost to the surroundings. To the surrounding environment. And ask for 4 assumptions. So our first assumption concerns energy. Now, apart from energy being lost to the environment, we can think more microscopically and imagine what happens to the particles of hot water and cold water as you pour the hot water into the cold water. As you pour the hot water into the cold water, the particles might, well, they will interact with each other. And what we have to assume here is that this process of mixing the two lots of water together doesn't add energy to the water. So we're saying that the mixing process doesn't add energy to the system. And this is important because in the real world, energy might be added through the mixing process, but that would complicate, or that will make the calculation extremely complicated, which we can't deal with our simple model. So these two assumptions deal with energy. Now, what other assumptions? We need two more. So what other assumptions need to be made for us to solve this problem and work out how much water needs to be added? So we've talked about energy, and that's all good. Remember that in order to calculate the amount of mass that we need to know the specific heat capacity of water, and we need to use this relationship, which we have done in class last week. Change in heat is going to be equal to the mass multiplied by the specific heat capacity of water multiplied by the change in temperature. Okay, so let's look at these variables. Heat energy, we know that the heat energy is transferred from the hot water to the cold water, and that's to do with energy, and we've taken care of those assumptions already. Now the mass, do we know the mass of the water? Let's see. The question doesn't tell us the mass, but it tells us the capacity. So we know there's 53 liters of water. Now, remember how I said that water, the density of water means that 1 kilogram of water is exactly 1 liter. And that only applies for pure water. So what we have to assume here, if we want to say, well, let's say this is 53 kilograms. 53 kilograms. It will be true if the water was pure. So that's one of our assumptions. The water is pure, and by pure I mean just H2O and no other impurities, which in real tap water does exist. Now what else do we have to assume about the water? Let's see. We're assuming that 1 kilogram or 1 liter is 1 kilogram. And this has to do with the water itself. So we have two assumptions about energy and two assumptions about water. Now, assumptions are really important when working with models, and everything in physics is based upon a model. So we're assuming, okay, this is how the real world works, and we model it using whatever model we have. In this case, we understand the law of conservation of energy, and our model has to take that into account, because if energy escapes, then this equation won't be true anymore. And we can't apply this if we don't know the mass. So the other two assumptions about the water take that into account. Okay, I think I've gone for too long now, so I have to make a separate recording to do part B. So I'll see you in a bit.